and you would be playing with my blood. You probably would have taken great delight seeing one of my past students, his name is Farouk, coming in to draw my blood, and me almost fainting every time he does it, even though he's so good about it. But you'd be playing with my blood, and I want you to pretend tonight that you are playing with my blood. The pictures that you're seeing are the exact pieces of equipment that you'd be using in our lab. And I know it's not replacing that real experience, but I do think it's still pretty good, even for an online lab. The first experiment we're going to do is count red blood cells, and then we're going to count white blood cells. You can read about the procedure and what I would have done with the dilution in your lab manual, and you still should. You should still know what I would have done with my dilutions. That's still fair game for the lab exam. The first one, like I said, we're going to do the number of red blood cells, and then we'll move on to white blood cells. These are common cell counts taken, especially when a doctor orders a complete blood cell count. The number of red blood cells in a typical microliter, and another way of saying that is cubic millimeter, is about 4.5 times 10 to the 6. That's 4.5 million. Now, I want you to look in your lab manual or even on the screen here, and you can see that I have a period, labstestonline.org. Now look at that tiny little dot, that tiny little period. In that tiny little dot, there would be 4.5 million red blood cells in that tiny little dot. That's a lot. You have about 200 different types of cells in your body, and you are about 100 trillion cells big. 1/4 of all of those 100 trillion cells are red blood cells. Red blood cells are our most abundant cell type. For white blood cells, the number of them is much lower. In a typical microliter, you have about 6,000 to 9,000 white blood cells. Now, we're going to start with our red blood cells. And I just told you what a normal red blood cell count would be. And it's written as the number of red blood cells over a cubic millimeter. Another way of saying that is a microliter. And this is a large number. I mean, if we counted just 1 microliter and counted 1 cell per second, it would take us 4.5 million seconds to count just that 1 microliter's worth of red blood cells. The semester would be over by the time you finished, probably. We're not going to count all 4.5 times 10 to the 6. We're going to dilute the solution. I am going to be using in my lab, when I dilute your solution for you tonight, I'm going to be using Gower's solution. What is the role of Gower's solution? The Gower's solution is to keep the red blood cells happy. It is an isotonic solution. So it dilutes them and keeps them happy. They're not going to rupture. We're also not going to count, in addition to this dilution, we're not going to count a cubic millimeter's worth. Remember, a cubic millimeter is a millimeter in width, length, and height. We're not going to count this entire volume. We're going to count smaller volumes. And as such, when we get our cell counts from the hemocytometer, which is what this slide is on the bottom right picture, we're going to have to back calculate. We're going to have to take into consideration this dilution and the fact that we did not count a full cubic millimeter in volume. The dilution I'm going to do for you is going to be a 1 to 200 dilution. This is, again, a picture of a hemocytometer at the top left picture. You can also see it drawn in a schematic way down at the bottom. It's a thick glass slide, and it has 2 metal plates. And on those metal plates, you could do 2 different counts. In the top left picture, underneath the hemocytometer slide, you're seeing what looks like glass rods that seem to have a little bubble in them. You're not going to believe this, but it's true. When I first started at Saddleback, the students were doing these dilutions. They were diluting my blood. And the instructor before me, her blood. And the students were using these mixing pipettes. That's the glass rods you're seeing in front of you. They were mouth pipetting these blood dilutions. Can you believe that? That was how they did it. So I come into the lab and the instructor is saying, yeah, that we mouth pipette. And I'm like, we don't mouth pipette in a lab, number 1. And number 2, we sure as hell don't mouth pipette somebody else's blood. Absolutely not. So we no longer let you mouth pipette. Yay. I do the dilutions for you. And again, I'm using this Gowers solution that is isotonic for the red blood cells. Now on the metal plate there's a grid etched into the metal plate, and you're seeing a picture of this grid in the bottom left picture. Let's look at it in a greater detail. It's the same picture that's also in your lab manual. So this picture in the top left is showing you this grid that is on these metal plates. And if you look at the very center square where I have it outlined in red, you are seeing that center square is a millimeter in length and a millimeter in width. Within that red center square, you're seeing 5 smaller squares with an R in them. And those smaller squares are the squares we're going to count. So we're going to count 5 squares, not this large big square. Remember, we don't want to be doing this the whole semester. And those 5 smaller squares have the following dimensions. They have a width of 0.2 millimeters, a length of 0.2 millimeters, and when the cover slip is on, we get a height of 0.1. So notice, even though we're counting 5 squares, the actual volume of these squares is 0.004 cubic millimeters. All I did was multiply 0.2 to 0.2 to 0.1. That's how we calculate volume. So we're counting a much smaller square, and we're diluting our red blood cells, a 1 to 200 dilution. Here's where we begin counting. You might have a better experience if you download this PowerPoint to your computer and expand your picture. If you don't have that ability to do that, I'm going to expand my picture. You're going to be counting the 5 squares that are outlined in red. Notice that those 5 outlined squares have 4 rows of 4 of smaller squares within them. Yes, you count all of those 16 smaller squares within that red square. If a red blood cell lands on the top perimeter or bottom perimeter, you have to decide which one you will count and which one you won't. If a red blood cell lands on the left perimeter or right perimeter, you again have to decide, and you have to stick to that choice. So for example, I count red blood cells that land on the top line and the left line. I do not count the red blood cells that land on the right line and bottom line. But you can choose. It has to be top or bottom, left or right. So go ahead and count the red blood cells in these 5 squares. Write down those 5 cell counts in your lab manual. You're going to need them later. And let's see how close we get to each other with our cell counts. Again, I'm going to expand my screen so maybe you can see these a little bit better. There. That's the most I can expand it without the squares getting out of your view. Go ahead and take about 5 minutes collecting this data, and then we'll crunch it on the next slide. So on the next slide, here's the equation that you will be responsible for on your lab exam. On your lab exam, I will tell you how many cells you counted, how many squares you counted, your dilution factor, and the volume for each square. All you have to do is plug and chug. So take a moment now to calculate your red blood cell count on this person. Did you add up, first of all, did you add up all 5 of your squares?
Yes.
I mean, what was the total cell count for you all, just counting the 5 squares? Where were you?
I got 446.
Okay.
I got 436.
Yeah, 436.
So the
34.
Monday, Wednesday class was very comparable to what you all are saying. Some people were in the 430s, and some people were up in the low 500s. That's pretty reasonable. When I counted, I got 479. So we're within range of each other. That's good. That tells me that you did it right. So what you're going to do now is take your cell count, the ones that you just told me. You're going to multiply by 200, which is our dilution factor. And you're going to divide by 5. That's the number of squares we counted. And you're also going to divide by the volume of the individual square, which was, I'll remind you, 2 slides above, 0.004. There it is in the blue square, text square at the bottom right of the slide. Now the next cell count we're going to do is a white blood cell count. And with the white blood cell count, we are not going to dilute our solution as much. We're only going to dilute 1 to 20, so 1 to 20 dilution. We're going to use a different solution for this dilution. We're going to use Turk's solution. And Turk's solution does 2 different things for us. It is going to, 1, lyse the red blood cells. It's not isotonic to red blood cells. So the red blood cells will be lysed, and that means they're going to be out of our way. And the Turk solution is going to also, secondly, stain the nuclei of the white blood cells, so it makes it easier to see. Now I say that, and yet the 4 squares that you're seeing on the slide here have white blood cells. And it's not the best picture, but we've tried to circle what these white blood cells look like in 2 of the squares. So in the top left square, you can see that I have a number 2 with a red circle by it, and that's because there were 2 white blood cells close together. Then a little over to the right, you're seeing another circle with a number 3 above it. And believe it or not, there are 3 white blood cells within that circle. You're going to be counting the 4 large corner squares that are shown on the hemocytometer grid. They're the ones that have the W for white blood cell. And these squares have the dimension of 1 millimeter by 1 millimeter and a height of 0.1. So we're going to have a different dilution factor. We have different volumes, and we're not counting as many squares. I'm going to expand my screen. Do your best to count the white blood cells, the little dots that you're seeing here. Take about 5 minutes to count, and then we'll see how close we get to each other. A normal white blood cell count is 6,000 to 9,000 cells per microliter.
Okay. Thank you.
You're welcome. Again, you're going to pick 2 of these slides, 2 of the abnormal slides, draw them in your lab manual, and also in your lab manual, it asks you to consider sources of error when you're doing these cell counts. And there are questions about what kind of abnormal cell count would you get if your instructor drew up an air bubble when she was drawing up the diluent. The diluent is the solution that's either Gowers or Turks that I used. So if I draw up an air bubble, am I drawing up enough of the diluent? I am not. The air bubble is taking up some of that volume, so I'm not diluting as much as I should. If I don't dilute as much as I should, then will I have a higher or a lower count?
Lower?
Higher?
If I don't dilute enough, remember, a normal red blood cell count is 4.5 million per microliter. If I don't dilute your red blood cells enough, you're stuck in the lab counting longer, aren't you? So the count would be elevated, abnormally elevated. If I draw up my cells, see, when I mix the diluent and the cells, I put them in a dish so I can mix them up real well. If I suck up my cells and I also have an air bubble, have I pulled up enough cells? And the answer is no, because I pulled up an air bubble, not the entire sample of cells. So in that case, because I'm not putting enough cells into my mixture, I'm overly diluting them, and you're going to get a very low cell count. There's also a question about what will happen to your cell count, because you put the cover slip on, you might get an air bubble trapped underneath your cover slip. And what would that do to your counts? And a lot of students don't know what an air bubble would do when it's trapped under a cover slip, but air bubbles kind of push all the cells away. So you would not count as many cells as you should if you've got this big air bubble that's sitting on top of one of the squares you're supposed to count? Those are questions that are in your lab manual under on page 39. You should pay attention to those. Now the next experiment we're going to do is hemoglobin content. And this is a very quick lab when you do it face-to-face with me. As in, here's how long it lasts. You come up to me in the lab. Do you see these pieces of paper on the picture? So you bring me one of these squares, these small squares of paper. It's special paper, and it's called a Tallquist test. And I squirt my blood onto this paper, and while the blood is still wet, you sit down at your desk, and you see this card behind the paper, and the card has color swatches on it, different color blocks. So you sit down at your desk, and you take this blood sample of mine, and you look at the redness of the blood sample, and you match it to the color swatch that you think it matches best to. So take some time, figure out which of the blocks above the blood sample you think matches the blood sample, and then you should write down in your notebook the two values. You should write down the hemoglobin grams percent value, and you should write down the percent normal value. And if you are following along in your lab manual, you are now on page 42. And taking this data, you would put it in your lab manual under procedures number 1. Let me explain what percent normal means. Let's say this blood sample on the square down at the bottom of the slide is mine. Which color swatch do you think it matches to the best?
90.
90.
Normal.
90.
Okay, so I'm hearing people saying that it's the 90% normal, and that grams percent that's in the box below it is 14.1 grams percent. Now, if I am a woman, so me having a hemoglobin of 14.1 is within normal range, and I would be in the 90th percentile. There would be only 10% of other women with a higher hemoglobin percent than me. So we want to know the raw score, that's the grams percent, but we also want to know where this person lands. If there were 100 women in a room, where would mine fall in the average of those 100 women? And I'd be in the 90th percentile. Again, only 10% of the women would have a higher grams percent than I would. So, hey, if you were in the 90th percentile after your first exam next week, would you be happy with that?
Yes.
Yes.
Of course. Me too. But some of you in the audience are a little freakish, a little Hermione-ish, from Harry Potter, and you can't help yourself if you're not the top student. Got to be the top. I'm going to find out who you are. So if I come in at 90%, I'm okay with 10% of the other women being a better hemoglobin grams percent than me. I consider myself normal and on track. I'm good. I don't need to be competitive. Now, in your PhysioX, another one that you're going to be doing, you don't use the Tallquist test. Instead, you use a machine called a hemoglobinometer, and I'm going to talk about that in just a moment. But in your lab manual, the hemoglobin grams percent in your lab manual, you're supposed to multiply it by the amount of oxygen that can bind to each gram of hemoglobin. Again, that number would be 1.34 milliliters of oxygen for every gram of hemoglobin. And this determines a patient's oxygen carrying capacity. The strictest definition of anemia is a reduced oxygen carrying capacity. That's the strictest definition. Some textbooks say it's a reduced hematocrit or a reduced red blood cell count. You can have a patient with a normal red blood cell count and a normal hematocrit, and they can still be anemic. The best example I can give you would be G6PD deficiency. I hope you've already watched your red blood cell lectures. In G6PD deficiency, the person's iron within the hemoglobin molecule is not in the correct ionic state. It's in a +3 state, and iron cannot bind to oxygen in that +3 state. So that would be a person that could have a normal red blood cell count and a normal hematocrit, but clearly has a reduced oxygen carrying capacity. So remember that 1.34 milliliters of oxygen for every gram of hemoglobin. That's an important number to know for this class, but also clinically. Again, the PhysioX, as I mentioned before, is going to use a hemoglobinometer when you do that experiment. And a hemoglobinometer looks like, what were those things called? You know, those little kid cameras where you actually put in some little discs and you clicked on the little wheel mechanism and it was like watching a slideshow. Anyway, the hemoglobinometer looks like one of those. You're going to look into this little machine and you're going to adjust a color filter. So again, it comes down to matching colors, just like you did with me a few moments ago. But the hemoglobinometer is using a different filter. You're going to be matching green colors. So I just don't want you to be surprised when you do that lab for PhysioX, thinking, oh, it's a totally different type of experiment. It's the same experiment. You're still figuring out hemoglobin grams percent. You're just using a different method. And if you want to watch a video on how this hemoglobinometer method is used, we have a video here for you. Okay, we have 2 more experiments to do. Hematocrit. On the next slide, you're going to measure my hematocrit. If we were doing this face-to-face, I would be taking these very small glass capillary tubes, and you can see this in the top middle picture. You can see the person's thumb holding this glass capillary tube. It's very small, very slender. And you can also see it down at the bottom left picture as well. So I would be filling these tubes with blood, and you can see at the end that there's a little white tip. That's a wax plug. And then I would be putting these tubes in a centrifuge for you all, and I'd spin them all down, and then I would deliver one of these capillary tubes to each table, and you would measure it. You're going to measure the packed red blood cell volume in millimeters, and you're also going to measure the entire whole blood sample in millimeters. You're going to divide the packed red blood cells by the height of the whole blood sample. You're also going to be asked to do a correction. This 0.96. It means that 96% of your hematocrit, when you're looking at the red blood cell volume, it's 96% pure. But there's still a little bit of plasma that might still be in between those red blood cells. And adjusting by this 0.96% accounts for that little contamination. So here's your sample. Go ahead and take the hematocrit. Notice that we're asking you to start at the end with the wax plug, even though it technically is not part of the red blood cell column and technically not part of the whole blood column either. When you divide those two numbers, that wax plug part is going to basically null out. So it's okay to include it as long as you include it in both. The website that you're seeing down at the bottom of the slide is a website I do recommend. It's free and it has really credible information. And one of the things you can look up at getbodysmart.com is how to do this hematocrit reading. They have other videos that you might find useful for other science classes as well. I hold this website in high regard. It's very simple. The videos are short, and they are showing you correct information. Remember to measure in millimeters. The ruler that you're seeing on your screen has increments of centimeters, so make sure you remember how to count in millimeters. And where you would be writing down your information in your lab manual would be on pages 44 and 45. Okay.
Can anyone else get 50?
So I would be dividing, for me, 37 millimeters divided by 76. So yes, approximately 50%. That's before doing the 0.96 adjustment. So when I actually do the math, I get about 0.49. And then if I multiplied that by 0.96, I get 0.47.
Are you gonna want us to know the equation for this as well?
You mean this division problem? Yes.
Yeah.
Yeah. Okay.
You ideally, in a perfect world, I don't think you would have to memorize it if you know that the definition of hematocrit is you're dividing your red blood cells by your entire whole blood sample. So you're trying to see what fraction of your whole blood sample is just red blood cells.
Well, thank
Well,
you.
thank you.
Sure.
Cara, really quick.
Sure.
The information that you said on the lab manual on page 44 where we would put in our information, I was just curious, are we turning in that information at some point, or are we just writing it down for ourselves?
You are absolutely turning this in, because in your lab manual, there are other questions that we ask of you about this data, and those are study questions for your lab exam. So you're going to be going through your lab manual and making sure that you finish answering all the questions that go with tonight's labs that we've done.
Is there a due date with them, or are we just, or is that until later?
The due date for your actual lab manual is the day of your lab exam.
Okay.
Mm-hmm.
Thank you.
You're welcome. So to get back to this equation is the same kind of equation when you think about what grade you get on a test. If you have 100 questions worth 1 point each on a test, and you get 60 correct, what percent did you get? 60%. So this is the same kind of equation. The height of the total sample, think of that as the size of your test. How many possible points? The height of the packed red blood cells, think of that as how you performed on the test. How many did you get right? So you divide how many you got right by the size of the entire test. It's the same equation, really. Okay, our last lab in our last 15 minutes left of class is blood typing. And maybe you haven't gotten to the blood typing lecture yet, but this is a slide with 3 blood drops on it, and there's a piece of paper held behind the slide so that you can hopefully see the agglutination. Agglutination means that you have had an immune response. Agglutination happens between an antibody and an antigen. On the red blood cells, we have antigens. When you watch that blood typing lecture, you learn that the antigens are sugars that are on our red blood cell membrane. If you have blood sugar A, you are blood type A. And the sugar for blood type A is N-acetylgalactosamine. If you are blood type B, then you have a different sugar on your red blood cell membrane, and that's galactose. If you're AB, you would have both of those sugars present. If you're blood type O, you don't have those sugars present. If you say you are A positive, the positive part means that you have this protein threaded through your red blood cell membrane called the Rh factor. Sometimes it's called rhesus factor. Sometimes it's called Rho factor. Sometimes it's called factor D. The reason why it's called RH factor or rhesus factor is because the person who was studying this RH factor was first identifying it in rhesus monkeys. So that's where the RH comes from. It's difficult to see on the slide, on this slide, but this person has agglutination on the anti-A side, and they have agglutination on the anti-D side. And this person is A positive. Let's look at other samples that are easier to see this agglutination. This slide is much better. Here are blood samples from 2 instructors. You pick either instructor 1 or instructor 2 and try and blood type, determine their blood type. Wherever you see clumping, wherever you see those clumps of red blood cells, that's the immune response. You added the antibody and it attacked the red blood cell antigen. We say you are what you clump. So if you clump with anti-B, it means that the B antigen must have been there. So go ahead and pick one of the instructors and try and tell me if you picked instructor 1. Go ahead and type it in the chat box what you think instructor 1 is. Correct. What I am seeing there, yes. All right, what about instructor 2? What do you think instructor 2 is? That one's a little bit more challenging. Yes, you are correct. Instructor 2 is O negative. They did not clump when you added anti-A, nor anti-B, nor anti-RH. Good job. Now, here's some more practice. Again, for your lab manual, Omar, since you asked, you're going to pretend you're taking instructor 1 or instructor 2's blood and you're pretending that it's yours and you're blood typing them. Here are 8 more samples to practice with, and you can determine the blood types of these 8 samples. And if you click on the notes section in this PowerPoint, you'll see the answers to these blood types. Now again, you're going to be doing a Physio-X on this. And when I talk about the Physio-X, I give students a challenge. My challenge is, if you really want to know your blood typing, you should be able to, number 1, identify the person's blood type. On this slide, you can practice with 8 different samples. So that's number 1, identify what blood type they are. The challenge comes from number 2. Then tell me what antibodies that person would have in their plasma. Then, challenge number 3, tell me what blood types that person can safely receive. And challenge number 4, what blood type, what people could receive blood from this person. So identify their blood type, tell me what antibodies they would have in their plasma, what blood types they can safely receive, and who can safely receive from that person. If you can do all 4 of those questions for these 8 blood types that you're seeing, then you understand, number 1, blood typing, and number 2, how to safely give someone a blood transfusion so that you don't give them incompatible blood. So, Omar, because you asked the question, I'm going to say it again to everyone. Yes, we just did 4 labs together tonight. And you collected data. But there are still more questions that need your attention. The questions in your lab manual, just to give you some history. When I first started at Saddleback teaching this class, there was no lab manual like what you have in your hands right now. Students had to keep a lab notebook. I'm sure many of you have taken micro and you know all about your lab notebooks. In most science classes, you were expected to keep a lab notebook. That's what science classes are about, this lab notebook. Documenting your results like a scientist should. So the students had to do a pre-write, where they basically had to rewrite in their lab notebook all the steps for the procedures they were going to do. They then had to collect their data, do a proper analysis and conclusion, right? Your standard science lab write-up. Introduction, purpose, procedure, analysis, conclusion. There was no lab exam separate. When I first started, there were only 2 exams for the entire physiology semester. Two. A midterm and a final. Only 2. Could you imagine? And for the midterm, you had both lecture and lab questions together. Same for the final. It was awful. It was horrible. And you got graded also on this lab notebook. And you had, when you did the experiment, you had 1 more class time to come back to the professor with your analysis and conclusion finished. You would come up with your lab notebook and I would have to check it off that you did it all. And then right there on the spot, right then and there, I would start giving you an oral exam on the lab techniques, right then and there. And if you did not pass the oral exam, you were handed back your lab notebook and you were told to go back and redo it and then try again. It was awful. It was not a good system. So that's why we have this now, the lab notebook. You don't have to do a pre-write, because I think that's a waste of time to rewrite procedures. And students said, well, if we're now having separate lab exams, is there a lab study guide? The questions that you answer in this lab notebook were written by me as a lab study guide. You want to know what I'm going to go after on your lab exam? Right there. That's what you look at. So of course, you want your lab notebook finished before your lab exam, because otherwise, how are you going to know what to study? And you should be rewarded for that work. This is, again, 10% of your grade, just for filling in your lab notebook. You do not get marked down if you answer a question incorrectly. You get marked down if you don't finish your lab notebook. Are there any questions about that? Okay. All right, well, we're at the end of our little experiment, online experiment. Again, there are more questions for you to look at in the lab manual. And there are, I want to warn you, on pages 45 through 47, there are some calculations with equations, and students get very nervous about them. And if you look on page 47, the very top, it says, you do need to know what these values mean, what their significance is, and what normal ranges there are. But you do not need to memorize the formulas for obtaining them. So you have to do the calculations, but you are not expected to memorize them. And again, those are the calculations found starting on page 45, where it says questions, calculations, and discussion. So from that section through page 46, you do not need to memorize those equations. All right, and then we have, if you really need more practice beyond your lab manual, we do have some more practice. Blood typing, like I showed you there, and some more analyses for red blood cell counts and white blood cell counts. And here are your normal red blood cell indices that we do expect you to know. Again, that is discussed, this slide is basically discussed on pages 45 and 46 of your lab manual. Any questions in our last 3 minutes together?